But we're going to get started here with a session on accelerating the data center edge. My name is Alex Snoor, and I'm a professor of computer science at UC San Diego. And I'm looking forward to introducing the next 4 talks. So the first talk is going to be given by Jia Zhe, who's a network technology engineer at Tencent, where he develops cloud-related products. And he's going to give us a talk on Turbo, which is an efficient communication framework for a large-scale data processing cluster.
Thank you for the invitation. I'm Xu from Tencent Company. Today, I would like to talk about our work, Turbo, which processes an efficiently communication framework for a larger scale data center processing cluster. This is a joint work with my Tencent colleagues, Lixiang, Zekun, Yachen, Chongqing, and Zihao Bin from NVIDIA. Note that Zhiyi and Peng Chao performed this work during an internship at Tencent. With the development of AI chain and high-performance computing, the global data volume is increasing significantly every year. The increase in global data volume also led to an annual increase in the number of servers. A larger server cluster requires stable and high-performance network communication guarantee. In this context, RDMA networks has been widely deployed. We can see that the procurement and the deployment scale of RDMA NICs is also increasing year by year. Is there no problem after deploying the RDMA devices? Based on our observation, this is not true. We observed a larger amount of data from online networks and summarized the common requirements and challenges in larger scale RDMA networks. Firstly, the communication performance the RDMA networks has not been fully utilized. As shown in the figure on the left, when the number of executors exceeded CC4, the task completion rate does not increase. The above problems stem from occupation of NIC memory, resource, and competition for server computing resource. Secondly, network load is uneven. Monitoring a cluster size of over 300 nodes, nearly a quarter of network load is unbalanced. This is due to the complex network architecture and network devices configuration in larger scale environment. Finally, the efficiency of application communication middleware is relatively low. In the case we observed a relatively high frequency of application exception resulting in uneven task completion time. This is due to the blocking communication middleware. This is due to the blocking of communication middleware, leading to low efficiency in both computation and communication. There are currently some challenges to address larger scale QP connection and memory usage, such as software hard combination solutions. The main idea is share UD of RD connection on middleware of NICs. Flux use the partitionally shared model. It departs from the conventional RDMA design by enabling connection shared among threads. FSST is choose one-side RDMA for fast RPC using two-side unreliable datagram. SIGCOMM' RPC introduce connection grouping and visualize the mapping to efficiently share the hardware resource between the concurrent client. In SRD, one connection endpoint can communicate with all other endpoints without creating an endpoint for every connection. The current plan brings many problems, such as application of driver modification required, increase end-to-end latency, overhead back to CPU, and so on. The current solution by load balancing mainly using end-to-end network collaboration solutions, which include packet-based solution, fluid-based solution, and the flow-based solution. Solr is packet-based solution. It disseminates packets over multiple paths in favor of paths with low average RTT. All function knowledge of let flow resets at the switch. The switch picked an outgoing port at random amount available choice for each flowlet. Typically, for flow-based solution are MP RDMA and Slim Fly. MP RDMA presents a multiple path transport for RDMA, which efficiently utilizes the rich network paths in data center. The current plane brings many problems, such as centralized fabric controller required, and hosts mechanism required end-to-end feedback. Switch mechanism requires hold-by-hold feedback. Out-of-order packets need to be routed by NICs. We propose turbo which use dynamical connected transport and random ports to solve the problem of excessive QPs and load balancing. DCT dynamically establish QP connection as needed. Specifically, DCT requires sender to maintain DC initiator and receiver to maintain DC targets. One new data block of flow arrive, we use DCT to dynamically establish a new connection transport. As shown in the middle figure, there are two Ethernet points, ETH0, ETH1, to transmit data blocks in each node. However, all blocks are mapped to the same egress port by ECMP, resulting in load imbalance among those ports and finally affecting the total throughput. Next, we use the DCT with random ports since each data block is transmitted in a flowlet. When the server assigns a random source port to the flowlet will be mapped into one of the two links. Note that the new flowlet will be initiated by DCT until the preceding flowlet for the same source and destination has been completed. Therefore, our block-level load balancing approach, flowlet will not introduce additional overhead to address rerouting issue. Yeah. Specifically, we divide a flow into multiple flowlets using DCT, with each flowlet transmitting the point party of the data block. The new flowlet transmission pattern allows us to achieve a more fine-grained load balancing, namely block-level load balancing. So we integrate a dynamical source port selection to change the data transmission path for each flowlet. Our design is simple but effective in practice. Yeah. To optimize the communication middleware, we use a big data processing system as an example. The shuffle read process set synchronize the meta information, block ID, block address, and so on, through a global metadata database. While the shuffle read process fetches the request data from other node according to the metadata information. Each worker requests at least one QP connection to send and receive data block. However, each worker is bound to the specific executor. There is mutual waiting between communication and computation. To address this challenge, we use Turbo to design a no-blocking communication middleware. When the executor completes the calculation of the data block, it will submit the metadata of the data block to the worker per thread for transmission. The decoupling of the worker and executor enables the overlap between communication and computation. In some cases, certain worker may become fully occupied, causing data blocking to waiting for a long time for transmission, while other workers remain idle. To address this issue, we designed a gate mechanism to allocate the data transmission request from executor. The gate mechanism assigns new incoming request to the worker with the least workload. Additionally, the gate mechanism balances the workload among the workers and use a wake-up mechanism to fully use the NIC resource. Executor thread will lock the data during the shuffle operation. When the executor thread is abnormal, the data cannot be accessed by other executor. To address this, we define an external shuffle server in RDMA called RDMA ESS. As shown in the left figure, each executor rejects the metadata of its data block to the RDMA ESS. When the worker in node 2 needed to fetch the data block from node 1, it sends a data block transmission request to node 1. And then the RDMA ESS worker in node 1 looks up the corresponding data block and sends it to node 2. In this way, the executor of Spark ESS will not lock the data block, as shown in the red figure compared with Spark ESS. Spark ESS can issue high system robustness even in the event of threat level failure. Turbo takes advantage of the flowlet transmission partner to achieve the block level load balancing. However, frequently establishing and releasing the connection for a single flow brings a lot of overhead. Yeah. To address this, the sender sends the data block immediately after sending the request packet. Therefore, Turbo can minimize the overhead introduced in connection established. When the receiver does not have enough on-chip memory to establish the QP connection, it will reject the connection as shown in the left finger. The sender will reconnect the receiver by waiting for a time. In some cases, the data block may reach the receiver after the QP is successfully reconnected. In the middle figure, we regard the data block as ghost data block. To identify the ghost data block, we labeled the validated data blocks with the target ID. Since the ghost data block do not have the target ID, so the receiver can quickly identify and discard the ghost data block. Yeah. When network failure occurs, we use a request to manually resubmit the job, which can be time-consuming. To address this, we use TCP serving as a backup transmission choice. When the RDMA transmission fails, the job will not fail by using TCP to recover the connection. This is the setup. A small scale test bed consists of 87 nodes with AMD 64 core processing and 1 terabyte memory. We equipped each node with NVIDIA Connect 6DX consisting of 2 independent 100 gigabyte ports. As for our larger scale deployment setup, we deployed hundreds of server nodes equipped with the same RDMA NICs. We test our motivation result, load balancing, node scalability, tail latency, and in the large scale cluster. Yeah. To evaluate the overall performance gain of our proposed dynamical block level flowlet transmission mechanism, we measure the average bandwidth utilization during the job execution. The left finger shows that the average bandwidth utilization of DCT outperformed RC by 7.2%. Turbo further improved the performance, which outperformed RC by 15.1%. The higher bandwidth utilization indicated the Turbo achieved better balance in network load. The red figure shows the load imbalance grade of the nodes. We found that Turbo always performs better than DCT and the RC. This is observed indicate that Turbo have a more balanced bandwidth. Then we evaluate the no-blocking communication as shown in the left figure. The average bandwidth utilization rate increases by 7.9% using no-blocking communication middleware. This improvement is due to the turbo scheme efficiently balancing the workload among the workers and achieving parallelism between computation and communication. To evaluate the load balance in large-scale network, the red figure depicts the probability distribution of maximum utilization rates for all top of rank switch. A low maximum utilization value indicators are more balanced throughout between links in QR switch. We observed that turbo can achieve better load balance and network bandwidth. Yeah, we then studied the task scalability of turbo. As shown in the left finger, the job completion time of turbo decreases faster than TCP and RC as the scale of the cluster increases. Turbo can reduce the GCT by an average of 35 points per 1% and 23.9% compared to TCP and RC respectively. The middle figure shows the compared of TCP and RC. The completion rate of turbo is always higher than TCP and RC. Turbo introduces the no-blocking communication middleware. Therefore, the communication and the computation can be overlapped to fully utilize the resource in the cluster. For the multi-level connection guarantee, we evaluate the successful ratio of tasks by running job with different number of tasks, as shown in the red figure. Turbo ensures high system reliability through thread fault protection and network fault backup links. We have observed that performance of existing big data processing system is constrained by network bandwidth and communication middleware. In order to address this limitation, we propose Turbo, a solution designed to alleviate communication bottleneck. Turbo incorporates DCT and dynamic source port to balance network load, utilizes no-blocking communication middleware to enhance network throughput, and leverage ESS RDMA and multi-level connection to guarantee scalability and stability. Our experiments have demonstrated that Turbo outperforms traditional communication system, resulting in a 23.9% reduction in job completion time. In our future work, we plan to further investigate load balancing in the event of link failure and explore the application of programmable NICs hardware accelerating the module. This is the end of my talk, and thanks everyone for listening. If you have questions, please ask. Yeah.
Question?
Thank you for the very nice talk. I'm Gao Xiongzhen from Huawei Technologies. My first question is, how does Turbo achieve non-blocking in computation and communication? And the second question is, how to handle the out-of-order data packets with multipath transmission? Thank you.
Thank you, question. You know that we have designed the Turbo. Turbo can decoupling the worker and executor, enable the overlap between communication and computation. We also designed a gate mechanism to balance the workload to the worker. So the gate mechanism can fully utilize the network resource, and the communication and the computation can overlap. Yeah. For the second problem, you know the DCT use the dynamical connection established. It is necessary ensure that all data packets are transmitted before disconnecting. The next block transmission requests are establishing the link. Each data break transmission by DTT is single path and no packet or disorder. Yeah.
All right, well, let's thank the speaker again. Thank you very much.